today's video is going to cover chapter 5, section 2, the first part of it. Well, we're going to jump around a bit, but the first part of it, which is going to cover log functions. And then tomorrow we'll get into their graphs. So a log function is basically just another way of writing an exponential expression. You can go back and forth between log and exponential by moving around the parts of it. So if I had this on the left-hand side, y equals, this is read as log, the little letter is a base. So this would be log base A of x. And we can convert this to exponential by taking the base, coming over and picking up the variable that's here by itself, or the term that's there by itself, and then the log drops off, leaving what's next to it. So I'll do that again. If it's log base A of x equals y, the A comes over and picks up the y, and then drops off and leaves the x by itself. So let's say I had log base 2 of 8 equals 3. This 2 is going to come over and pick up the 3, drop off, leaving you with an 8. So here's that same expression. This would be log form, this would be exponential, and they're both true because 2 to the third power equals 8. So a lot of the basics of logs is just learning the conversion back and forth. The little number would pick up whatever's on the other side of the equal sign and leave the drop off, leaving that number by itself. Now let's say you start with your exponential function, like a to the y equals x. Remember, this is the base of the exponential function. That becomes the base on the log. No pair ever stays together. So we break the y up to the other side, the x comes over with the a. So this would be log base a of x equals y. So if I took this exponential function, 2 is the base, so it becomes the base on the log. The 3 goes to the other side, and the 8 comes on the side with the 2. So for all of these expressions or equations, we are converting from log to exponential or from exponential to log. The easiest way to identify the two is the word log in it. If the word log is in the is in the expression, then that is a log function and we're putting into exponential. And if it's not, then we're doing vice versa. So this first one says log base 2 of 8 is 3. This is one we just did. 2 would come over and pick up the 3 and drop off, leaving the 8 by itself. That's it. Convert to exponential. Go to 2. Now the base is 1/2. 1/2 comes over and picks up the negative 4. So 1/2 to the negative 4 equals 16. For now, that's all we're doing, just converting. Log base 10 of 100,000 equals 5. The 10 comes over and picks up the 5. Leaves the 100,000 by itself. Here we have an exponential function. Obviously, the word's not log in it. The word log is not in it. So 5 is the base. That becomes the bottom of the log. Log base 5 of 25 equals 2. Go to 5. 3 to the negative 4 equals 1/81. So 3 is the base. Log base 3 of 1/81 equals negative 4. 3/4 to the 0 power equals 1. The 3/4 is now the base. The 1 comes on the side with that, and the 0 gets bumped to the other side. These are the properties of logs. These properties are going to allow us to simplify. So we'll have expressions like log base 5 of 1. The equals x will be missing from this, and you're going to learn to use mental math to solve these. This first expression would equal would equal 0, because if there was an x here, let's say 5 to the x power would equal 1. Anything to the power of what gives you 1, and it's 0. So doesn't matter what the base is here. If the big number is 1, the solution to that, or the answer to that expression would be 0. If you look at the second one, log base a of a. So if the base and the larger number are the same, then my answer is 1. Because, again, if I had, let's say, 5 of 5 equals x, 5 to what power would give us 5? That would be 5 to the first. So if the base and the number next to it are the same, then it's 1. The third one says log base a of a to the x. So now the exponent here is my answer, because if this is rewritten as log base, again, let's try 5 to the x, whatever this is on the other side of the equal sign, so let's say that's y, 5 would come over and pick that up, and I'd drop off, leaving 5 to the x. So we just created the one-to-one property where those exponents would be equal. So if we compare it to the one that we just did up here, the exponent on this a would be 1. So the same rule applies. If the base and the large number are the same, we grab the exponent. On here, that exponent is 1. Any other number, and that would be the answer there. So if I had log base 5 of 5 squared, then my answer is just 2. And the one-to-one property works with the logs. If you have log of the same base, so let's say it's log of 5 of x equals log of 5, 2. If these logs are the same and the base is the same, then I set what's next to my log equal to each other, like x equals 2. So the more comfortable you are with logs, the faster you can do these. And again, it's a lot of mental math, the easier it will get. Here we go. So these all say solve for x, but you could also see all of this without an x and you'd still want to be able to simplify it. So if I had log base 2 of 32 equals x, I could come over here, 2 would pick up the x, leave 32. If you don't know the power of 32 as the base of 2, you could do 2 and 16, which is 2 and 8, which is 2 and 4, which is 2 and 2. That's 1, 2, 3, 4, 5 2's. So 2 to the x equals 2 to the 5th, and then x equals 5. Without the x here, if I just had log base 2 of 32, my answer is just 5. You don't need the x. You can just simplify it by saying 2 to what power gives you 32, and that answer is 5. So if I look at 8, 4 comes over and picks up the x. 4 to the x equals 2. And here's the scenario we had yesterday where we had to change the base to be the same, or the day before. So you can either change this to be 2 to the second raised to the x equals 2. This would be to the first, so then we'd set the exponents equal to each other. 2x equals 1, x equals 1/2. But another trick to learn is to get from here to that being its square root, that is raising it to the power of 1/2. So you can also do that without the change of base. So if I had log base 9 of 3, that's 1/2, because the square root of 9 would be 3. All right, looking at 9, 3 to what power gives me 1. This is my shortcut with the x being 0. If x is 0, then that changes the base to 1. Log base 10, which is also just log. So if you see just the word log by itself, which is what your calculators have, that is log base 10. So sometimes it's here and sometimes it would look like this, and these mean the same thing. Log without any base is log base 10. So 10 to what power gives you 1 over 100. I could bring the 100 to the top. 10 to the x would equal 100 to the negative 1. Change the base, 10 to the x would equal 10 to the second raised to the negative 1. So 10 to the x would equal 10 to the negative 2, and x would equal negative 2. You can also look at this as, if I had log base 10 of 1 over 100, how do I get from 10 to 100? It's squared. And how do I bring it to the bottom? It's negative. So negative 2 would be the answer. All right, 11 has another one with 1, so it doesn't matter what the base is. We would raise it to the 0 power to get it to be 1. And 12, let's see if we can do that mental math way. So how do I get from 5 to 1 over 125? The exponent has to be negative, and from 5 to 125, it would be raised to the 3rd power. If you don't see that, then change it. So it's 5 to the x equals 1 over 125. Bring 125 to the top. It would be 125 to the negative 1. And then 125 is 5 to the 3rd. So I'd get 5 to the x equals 5 to the negative third, and x would equal negative 3. All right, just some more examples here. So 13, same thing. We can convert this. 7 picks up the x equals 343, and 343 is 7 cubed. Again, that's a weird one. So if you don't know, divide it into it. It goes 343, 4, that's 9, and then 49 would be 7 and 7. So that's a good one to kind of just know that 7 to the third power. I would say you want to know most of your cubes, but 7 to the third power is 343. So 7 to the x would equal 7 to the third, and x equals 3. Or what power do I raise 7 to get to 343? And that's also 3. All right, 14, little different this time because the the variable's on the base. So x to the third equals 8 over 27. So I need to find something that I can raise to the third power to get it to be 8 over 27, or I can cube root each of these. And the cube root of 8 is 2, and the cube root of 27 is 9. So is 2 ninths to the third power 8 over 27? It sure is, so that's the answer. X would equal 2 ninths. Okay, 15. Now my base is raised to a fraction. So 4 to the 5 halves equals x. When we take that fraction to make it into the radical, the 2 slides over. So this is the square root of 4 raised to the 5th power. 2 to the 5th power, or 2 times 2 times 2 times 2 times 2. This is 4, 8, 16, 32. Look at 16. 49 to the power of x equals the cube root of 7. So yesterday or the day before, we talked about this being 1/3, 7 to the 1/3 there, because if it's a square root, it's 1/2. If it's a cube root, it's 1/3. This would be the exponent. This would be the index. And then I can rewrite 49 as 7 squared raised to the x. So I'd get 2x equals 1/3. Divide both sides by 2 or multiply by 1/2, and I get x equals 1/6. Look at 17, 5 to the x equals 1 over 625. I can bring 625 to the top by making it -1. And 625 is 5, and 125, which is 5, and 25, which is 5 and 5. So that's 5 raised to the 4th power, raised to the -1, which is 5 to the -4, and I get x equals -4. 18 is that base of 10. So 10 to what power is 0.001. So 0.001 is 10 hundredths thousandths. This would be 1 over 1,000 equals 10 to the x. I can bring the 1,000 to the top by making it a negative exponent. So 10 to the x equals 1,000 to the -1. And then for each 0 here, that's a power of 1 for an exponent on a 10. So this would be 10 to the third raised to the -1, which means x equals -3. So 10 to the -3 would be 0.001. All right, some more examples, and I think this is the last slide before we move into LNs. Yep, the last slide before we move into LN. All right, so 19, x equals log base 8 of the 4th root of 8. It's flipped around the order, but we still do the same thing. 8 would come over and pick up the x. So 8 to the x would equal the 4th root of 8. 8 to the x would equal 8 to the 1/4, and then x equals 1/4. 20. So 20 is the first time we have a log function within an exponential function. So this is actually exponential, not log. That's an exponential function being raised to log power. So if I wanted to convert this to to log, this is my base. I would get log base 3 of the number on the other side, which is x, would equal log base 3 of 8. And then because the log and the base are the same, I can set what's next to it equal to each other, and I get x equals 8. Now the shortcut is if the base here is the same as the base on the log, we can actually cancel through it and keep the number that is next to it. So if we base that, 2 to the log base 2 of 9 would actually cancel out, leaving me with just 9. If you don't see the shortcut, then work through it the normal way. So convert this to x. So this would be the base on the log. Log base 2 of x would equal log base 2 of 9. And then the one-to-one property says set what's next to those logs equal to each other. And I would get x equals 9. Okay, x comes over, picks up the negative 2. So x to the negative 2 equals 25. I can make this 1 over x squared equals 25. And then I can put this over 1, or I can cross multiply. 25x squared would equal 1. Divide both sides by 25. X squared would equal 1 over 25. And then I would square root, but I got to do plus and minus 1/5. 23, 4 picks up the 3, 4 to the third equals x, and 4 times 4 times 4 is 64. 24, 4 comes over, picks up the x, equals the cube root of 16. This would be 16 to the 1/3. Change them so they have the same base. 16 is 4 squared raised to the 1/3. So I would get x equals 2 times 1/3, or 2/3. Okay, so that's it for the simplifying of logs. We're going to skip ahead for the graphing. We're going to come back to this tomorrow. I want you to go to the natural log slide. So we're on slide 13. Just like e is the natural base, the log of e is called the natural log. So log base e of x is the same thing as ln of x. When you see log base e, it can get replaced with with ln. So everything we just talked about with logs have the same qualities as these natural ln's. So the graphs we'll work on tomorrow. But for right now, pay attention to all your little basic properties. ln of 1 would be 0 because log base e of 1 would be 0. ln of e would be 1 because log base e of e would be 1. It would be the exponent on the e. ln of e to the x would be x because log base e of e to the x, these are the same, would cancel, leaving you with just the exponent. And the one-to-one property says if ln of x equals ln of y, then x equals y, because if it's log base e of x equals log base e of y, we can ignore the logs and set what's next to it equal to each other. So the biggest one I would say is ln of e is 1. That's pretty commonly used. Just know that it would cross through and leave you with the exponent. That makes life so much easier. It's a lot. You can use those for a lot of shortcuts. All right, so solve for x. 29. ln of 1 over e equals x. So this is log base e of 1 over e equals x. E to the x would equal 1 over e. That's a negative 1, because to get from e to the bottom, it would be negative 1. Or if I pull this up to the top, it would be negative 1. Either way, x equals negative 1. 30 is e to the ln of 5. So this would be e to the log base e of 5. The base on the exponential function's the same as the log, so we can cancel it through and just keep what's next to it. X equals 2 ln of e. We just said ln of e cancels, leaving me with the exponent. So that would be 2 times 1, which is 2. If you don't know that shortcut, then rewrite it 2 log base e of e. The e actually comes over, well, you have to divide by 2 first. And then e comes over and picks up the exponent. And x over 2 would equal 1, multiply by 2, and x would be 2. So if you can catch the ln of e and cancel it, giving you the exponent, it's going to be much easier. 32, ln of e to the 1/3. Here we go. Cancel these out. Keep the exponent. 1/3 equals x. Long way around would be log base e of e to the 1/3 equals x. E comes over and picks up the x. Bases are the same, so you set the exponents equal to each other. 33, ln of e to the 1. So this here is 0 because log base e of 1, this is 0. 5 times 0 would give you 0 for x. 34, ln of e cancels, giving you 1. 3/4 times 1 is x, which is 3/4. And 35, e to the ln of 7. This is the same thing as log base e, and then the bases are the same, so we cancel them out. And I'd get x equals 7. We're going to save the graphs of ln for tomorrow's video. So that wraps up today. Submit your notes. And use the remaining time to work on the assignment, which is the 5.2a homework. Have a great day, guys.